Hi, alright, let's have a look at some algorithms. Now let's look at, remember before from asynchronous variable iteration for Markov decision processes, here's the algorithm when you store Q of S of A. So we initialize Q of A arbitrarily, and you can repeat forever, selecting a state and an action and updating the Q of the S of A based on the immediate reward, plus the maximum of the Q reward for the current state, but you do the expectation over all states. That's why the probability of S and A is there. Alright, so now let's do the first case of reinforcement learning for the deterministic reinforcement learning. And we're going to look at this as just asynchronous variable iteration. And the idea is that we're going to use asynchronous variable iteration to just learn the Q function. So like what we did before, we're going to initialize Q of S of A arbitrarily, but now we're going to choose the state and action pair according to the current state and the action we're going to choose. So we're going to repeat forever. We're going to select and carry out an action A, and we're going to observe the reward R and the state S. So this idea of repeating forever, selecting and carrying out an action, and then observing the reward and the state is a common theme amongst our reinforcement learning algorithms. So if we know this, then we know that because this is deterministic, we know that when we do action A in state S, we receive reward R, and we update state, we get to state S prime. Therefore, we can just use the asynchronous value iteration to go and update Q. So we're going to update Q according to that, and now we're going to change S to S prime. And this works for deterministic cases and is a common theme for cases like tic-tac-toe and other games where everything is deterministic. This works. And if you run it long enough, it just learns the optimal game. Interestingly, it learns the optimal strategy no matter what action you carry out, because it's trying to learn the Q function of the optimal strategy independently of what you've done. So now we have to worry about what to do when we don't have its deterministic. What happens when there is randomness, when there are stochastic actions? Right, so let's have a look at this. So before we do that, let's look at a simple case about how can we compute the average of a sequence of values. Suppose we have a sequence of values v1, v2, v3 that we're receiving a value all the time, and what we want to do is to get the running estimate of the average of the first k values. I'm going to call that A of k. So A of k is v1 plus vk divided by k. And this is often what we want to do if we want the expected value of something. We just want the average that we've seen so far. Well, we can do a little bit of arithmetic, and now suppose we know A of k plus 1, and when new value vk arrives. So now we're going to split it up into this case here about the ak minus the first k minus 1 plus the vk. And if you look at what this is equal to ak minus 1 times k minus 1. So if we do this, we end up with this is equal to k minus 1 times ak minus 1 plus vk divided by k. And so now we could actually just factorize these out into the two halves. So let alpha k be 1 on k. Then we can show that ak is 1 minus alpha k, so that's k minus 1 on k is 1 minus alpha k times ak minus 1 plus alpha k times vk. So in this way of viewing it, it's a linear interpolation between the previous value and the next value. And we interpolate as you get, its k increases as you get more and more data, you use the average more, and early on you can use the value more. The other way of viewing it is that we're going to start with the previous value, and then we're going to have this error term. How wrong is the new value from the old value? How bad was the old estimate? And so this is this error term, this TD difference as they're called, and we're going to multiply that by AK. So we're going to adjust AK, big A, k minus 1 by the error term times alpha k. That's often called the temporal difference formula. Now sometimes we're going to do this with alpha fixed. So often we're going to do this with alpha fixed, and we'll play around with what happens with alpha's fixed and alpha's not fixed in a minute. So it turns out you can guarantee convergence to the average as long as these two conditions hold. Some sense alpha k has to be big enough, so the second term is big enough so that we're going to keep counting those values, and the squared value's got to be less than it, so we're not going to be dominated by anything. So we're going to keep going. And one of the ones that we're going to play with that treats things works better is to treat alpha k as 10 divided by 9 plus k. Now this number here was chosen because the first case it's going to be 1. So in k is the first case, it's alpha k is 1 because we don't have any previous experience. And then after that, the new cases are sort of 10 times what they would be otherwise. So we're going to play with that. All right, so now let's look at the idea of Q learning. So what we're going to do is we're going to store the Q state action. I'm going to update this like we do in asynchronous value iterations, but we're going to use the empirical probabilities and reward. We're going to do expectations. So like in typical of reinforcement learning, was we have an experience which you're in state S, did action A, received reward R, and ended up in S prime. And then this is going to provide one piece of data to update Q of S and A. So this experience, S, A, R, S prime, provides a new value for the value of S prime. And so what happened was that we were in state S, we carried out action A, we received reward R, plus, and we ended up in S prime. So what the new value is, it's the reward plus the discounted future reward. So it's this immediate reward plus our new estimate of the future reward, which is the maximum over Q, and that's our discount factor. Now we're going to stick those two together. So we now have, this is the new data point, we're going to average it into the old value of Q. So that says the new value of Q is the old value of Q plus this difference. And this error term is the new estimate, which is R plus gamma of max of Q of S and A minus Q of S and A. So it's the new estimate minus the old estimate. We're going to multiply that by alpha, and we're going to use that as an error for the value of Q, and that's my new value of Q. So we put those together, here's Q learning. So we're going to initialize Q and S and A arbitrarily. We're going to observe the current state, and we're going to repeat this loop forever. We're going to select and carry out an action A, so we're in state S, did action A. We're going to observe the reward R on the state S prime, and we end up with this form. The Q of S of A is the old value of Q of SA plus alpha times this error. The error here is the new estimate minus the old estimate. And then we're going to move along so S becomes the old S prime. We're going to repeat this forever. Okay, so we're going to play with this in a moment. But what's interesting about this is this algorithm is going to converge independently of what action A we choose. So we didn't have to choose a good action, we just had to choose any action. So Q learning converges to an optimal policy no matter what the agent does, as long as it tries each action in each state enough. But then the question is, what should the agent do? And there's this dichotomy between whether we should exploit or explore. So when we're going to exploit, when in state S, we're going to select an action that maximizes Q of S and A. So that's the exploiting. That's the best action we could do in state S according to our current estimates. The other one is to explore, is just to select another action. So here are some exploration strategies to use. The simplest one is called the epsilon greedy strategy. We're going to choose a random action with probability epsilon and choose the best action with probability 1 minus epsilon. So epsilon is how much we're going to explore. So in epsilon small, we're going to explore a little bit and exploit, but epsilon could even be 1, and it's just going to act randomly. One of the problems with this is that randomness, it depends on how, one of the problems with this is that it treats all actions the same. So if there's two very good actions, one very bad action, it's going to choose the really bad action just as often as it's going to choose the next to best action. But you probably really prefer just to compare the top two actions. So another one to do is this softmax action. So we're going to choose them in proportion to their Q values. So higher Q values are more likely to be chosen. So here T is a temperature. When the temperature is very high, it's going to just act randomly. When the temperature is very low, it's going to select the best action all the time. And in between that, it's going to prefer more likely actions and less likely actions. Another one we'll look at is optimism in the face of uncertainty. So we're going to initialize Q to values that encourage exploration. So we're going to pretend we know what Q is. So we're going to pretend that everything we haven't explored is really good. And we're going to do that by making Q big. And the other one is to do upper confidence bound, we're going to take into account both the average and the variance. So we'd like to look at how we're going to not only look at the average Q value, but how much they vary, because it might be the case that something we haven't looked at, we're unsure about how Q it is, how good it is, and so we might want to change that. And the other one we might want to do is to maintain a stochastic policy, which is a distribution over actions. Alright, so let's have a look at this running. So let's go look at this running, and we get to alright. So here's a tiny game. So there are 6 states, 1, 2, 3, 4, 5, 6. Each of those square scapes is a different is a state. In each state there are 4 actions, and so that's all the agent knows. It just knows there are 6 states and 4 actions, and it knows what state it's in. I've named the states and I put them in 4 arrows, but they're called up, left, right, which you might expect. But the bottom one's called careful up. And we're going to learn, we might have some intuition about what these do, but these 4 actions here are just random names that we've given it. Okay, and so what we're going to do here is we're going to go, say we go left, and we got the last reward here was -1. So the Q value for this going left in this state is -1, and the blue arrows here now point to the optimal states. And we could go careful up, and careful up also received a reward of -1, and it went up. Okay, so it changed states. We could go right, and we're going to go right. The reward was was 0, and go right again, and the reward is -1, and we stay in the same state. If we go up, we move up a state, and so now we have this up in the top left, right state. We could go up and receive a reward of -1. We go right and receive another reward of -1, and we go left. So notice how in each of these states, the Q values for each of the 4 actions are shown. So if we go up here, we get -1. If we go right, we end up with 0. If we go left, we still end up with 0. We get a reward of 0. If we go left here, we end up with a -1. So we end up with 10. If we go up again here, we end up staying where you were. If you go up again, we went up twice. One time we actually went up, and the other time we didn't go up. And we could try going left here, and that's really bad. It's got a -100. We go up again, and we end up with this state here. And notice there's this 9 here, because it went up into a state which the maximum Q value was 10. So this looks like a very good state, and so going up here is good. We can go left here, and we get another 10. And now we could go up again, and all of a sudden we went from the bottom state into this middle state, and the middle state looks very good. We try going right here, and we end up going right. We could try going left here, and we end up with 8.1, is because it's been left here once, and it actually looks like a good state. So it looks as though it's good to go right there and up there. And we can go careful up, and now careful up looks good. Now we can go left again. Okay, so we can just keep going like this. So here's 400 steps of doing this, and it's worked out that the best optimal strategy is to, from the bottom left corner here, you're going to go up, then you're going to go careful up. And what careful up does, it actually gives you a reward of -1, but it deterministically goes upwards. But the up itself has randomly sometimes goes left or right. And so then we can keep going. Now that's 400 steps, but you can even try 1,000,000 steps. 1, 2, 3, 4, 5, 6. There's 1,000,000 steps, and we can do it pretty well, and it finds out the optimal strategy here is to go careful up and careful up. So careful up on the left and careful up on the right. So if you do it again, and after a little while it's going to converge, and it turns out this is the optimal strategy, is to go from the bottom left one, we're going to go up, and then we go careful up because it avoids us falling into this big trap, and then we're going to go left. Alright, so that's Q learning for us. Alright, so let's look at now some problems with this. So it only does one problem with it, is it only does one backup between each experience. So this might not be appropriate for a robot interacting with the real world. So you might want to learn lots of more information from one experience. So an agent can do a lot better use of the data by experience by doing a whole lot of other things. So here are some ideas we can do to improve the use of the experiences. So I could remember previous experiences and use these to update the model, which is called action replay. So you can remember them. So instead of only updating when we experience things, we can remember them. We could build a model and use the Markov decision process methods to determine the optimum results, or we could do multiple step backups. And the other problem with Q-learning is it's based on states, so we're learning separately from each state. So what we can do is we can now try and work out how to go about evaluating reinforcement learning. So here is the sort of thing we're going to do. On the x-axis here is the number of steps, and here it's in thousands. So we go from 0 to 10,000 to 200,000 steps. What's peculiar about this is it's going to learn for the first 100,000 steps, and then it's going to start exploiting 100%. It's going to just keep exploit at 100%. That's this plot here. And on the right and on the y-axis is the accumulated reward. So what's going to typically happens is it goes down for a while because it's learning, it doesn't work out what to do, and then it learns what to do, and after a while we get to 10,000 steps. It starts then having its optimal policy. It's not exploring anymore. So let's look at some examples of this. So here is here's the case of doing the AI space tools we're going to build. So if you go to aispace.org, aipython.org, we're going to find out this applet, and there's a whole lot of demos we have in there for reinforcement learning. So here's the reinforcement learning for Q-test. And so it's going to build us a test algorithm. And I'm just going to plot some things and tell you what they are. So this is for a simple environment, which will explain that. It doesn't really know what the environment is. And so if we do this, we're going to plot this algorithm. And here's what happens with a fixed alpha of alpha is 0.1. And so it goes down for a while, then it starts going up. So it has to learn for a while, then it starts going up, and it goes upright. It's quite noisy, so if we try exactly the same thing again, we find out that the next one, it actually didn't go as well, except it seems to might have learned a better policy. Alright, so we could try something else. We could try the case about doing alpha k is 1 over k. Alright. Whoops. So I messed something up here. We're going to copy that, paste that, and we're going to end up watching this again. And this is what happens when you have 1 over k. So 1 over k here didn't work as well as having this fixed k. Turns out that averaging these values doesn't work as well as one might expect it to. Let's try one more time. Alright, and so again what we have here is we have this red line, and both of these, the red and the green, seem to be learning a worse policy than it is with fixed alpha. Turns out we can, if you try and plot it with this other way to do this way to update alpha, is we're going to do this 1 over k plus 1. You find it actually works better than all of those, because it actually learns initially well, but it also gets a better policy in the end. And if you do exactly the same thing again, we're going to have it again. So notice what happens is even two different runs of the same case might end up with different policies. So these are all in pairs. So the first two were all of the same policy, and the second two were all of the same policy. So we can just play and explore how different values of alpha affect our reinforcement learning. Okay, so next time we're going to look at some different reinforcement learning algorithms.